calculator with you every day. We don't really have any chapters to read when we do stats. The general overview for each statistic will be given to you on handouts. So for example, you'll see among your many handouts this thing that says the t-test for 2 independent samples. About 3 pages long, and this is just an overview of the statistic that we're going to do and the assumptions of the statistic and things like that. You don't have to have read this to do what we're going to do in class today, but I encourage you to read over it tonight just so you have an idea, some background about this statistic. When we do stats in here, I'm not going to spend time going over these kinds of things about the statistic. We're going to spend our time in here doing math. We're going to do the stats in here because I want to make sure that you understand every step of what you need to do for every problem. Because once you learn the system, it works great. Okay? But you need to learn the system for surviving stats. Okay? And a lot of it is just to stay really organized and follow a pattern. So I have lots of patterns for you to pay attention to. And we'll go through everything nice and slow. If you need me to repeat anything at any time, you're still not clear on the concept, stop me, because this is not a time when you want to be like, oh, I'll figure it out later, because it will snowball into WTF in about 3 minutes. Okay? So make sure that if at any point you need me to repeat myself or go over something again, explain something a different way, ask. Zero problem with that, because if we can get a good foundation going today, the rest of the math will kind of roll right out of that. So we just have to get into the same habits so we can agree on what it is we're going to do. All right. So first thing I want to do is kind of connect you back with the last time you did stats in 3510. Now in 3510, you should have covered z-score for single sample. Did you do that? Yep. Z-score for single sample, figuring out where a particular score was in a sample, and you could figure out if z was 1 for that number, it was 1 standard deviation away from the mean. If z was 1.5, it was 1.5 standard deviations away from the mean. Remember that? Then you should have also covered z-score for sample mean, which is where you've got a distribution of sample means, all the samples of the same size, and you're trying to figure out where that sample is, your sample for your study is, relative to the mean for all of the samples of the same size. Now if you take a look at those formulas for z, you'll see that they look pretty similar. You have a score here, since we're doing z for a particular score, we've got x, then we're subtracting out the population mean and dividing by the population standard deviation. That's the basic formula for z. When we start doing z-score for sample mean, we just swap out the sample mean for the thing that we're looking to associate z for. Now we're going to use the population mean. Sometimes people will put this there, talk about the mean for the sampling distribution. The population mean and the mean for the sampling distribution are the same, so it doesn't matter which one you use there. It should be the same value. And divided by the standard error, which, as you can tell from the symbol, is based on population standard deviation. Now, if you don't remember what those different symbols are, you don't remember what they're called, if you look over to the right-hand column, I put all the notes, all the different symbols and what they're called, so if you can't remember, because you haven't used those in months, so when I use a particular term, or if you want to ask me about a particular term, you'll know what symbol goes with what definition. So is everybody, you guys kind of vaguely remember that z-score stuff? So those things are all, there's no terms in there that you're like, I don't know what you're talking about. We're all right with those? All right, now, I discovered during my last class that some people in 3510 did not do single sample t. Have you guys done t? With 3510, did you do the t-test for a single sample, the one right below that? Okay. Sort of-ish. Okay, well, the good news is that whether you did it or not, I'm not going to make you do it here. Okay. But what I want you to take a look at, this is really kind of a transition statistic. I want you to take a look at the formula for single sample t and compare it to the one for z-score for a sample. What do you see? It's really similar.
Different variables.
Slightly different variables. Instead, so that the mean is the same, right? We've got sample mean and sample mean. We've got population standard deviation or population mean or the mean for the sampling distribution, mean for the sampling distribution. The big difference I see is here on the bottom, right? Here we've got a standard error based on the population standard deviation. And down here, we've got a standard error based on the sample standard deviation. The reason that we shift from doing a z-score analysis to a t-test is because we don't know enough about the population to do a z-score. We don't know what the population standard deviation is. And if you don't know what the population standard deviation is, you can't do z. Because you have to have, whether you're doing z for a single score or z for a sample mean, you have to know what the population standard deviation is or you can't do the formula. But sometimes we don't know what the population standard deviation is. And if that's the case, then we have to shift over to t. Because t, what we know about is the sample. So the only difference between the t-test for a single sample and the z-score for a single sample is that what we're using to calculate the denominator goes from being the population standard deviation to get standard error to using the sample standard deviation to generate an estimated standard error, little s sub n. Okay, so that's what, you know you're doing a t-test when the denominator's got sample stuff in it, not population stuff in it. Now, what we're going to focus on in here is the t-test for two samples. Okay, that's the most common use for t-test. T for two samples. Okay, so when you have two groups, two treatments, two completely distinct groups, different subjects in each group, then you're talking about the t-test for independent samples. We can also refer to this as a between subjects t-test because you're talking about a t-test for a between subjects design comparing two groups. If, on the other hand, we're doing a within subjects design and we're comparing one group but with two treatments, then we're going to do t-test for related samples because the sample of subjects that experience treatment 1 is the same sample of subjects that experience treatment 2. So the samples for the two treatments are related. They're the same subjects. So the t-test for two independent samples, that's for a between subjects design. The t-test for related samples is for a within subjects design. Now let's take a look at this formula. That's what we're going to start working on today. The t-test for independent samples. Notice that in the denominator now, we have nothing from the population at all. We know 0 about the population. Now we don't know the population mean, we don't know the population standard deviation. So now all we've got to work with are sample means. So we're talking about two samples, so I'm going to have a mean for sample 1 and a mean for sample 2. That's what I'm going to have in my numerator now, instead of a sample mean and a population mean. Now it's just going to be two sample means. And we're going to tell them apart by giving them subscript, 1 and 2. Right? Love subscripts. All about the subscripts. Okay. In the denominator, we've still got that small s, that sample standard deviation as the underlying statistic. But now we're going to have to figure out, we're going to have to do something with that because we actually have two different samples, and each sample has its own standard deviation, and we're going to have to figure out a way to manipulate that information to give us a single denominator to put in for the estimated error in the bottom. Okay, so we're going to learn how to do that. But effectively, it's the same kind of formula we've been working with all along. Two means on the top, and some kind of standard deviation thing turned into a standard error thing on the bottom. All of these formulas have that pattern. And on this chart, what I've done is, this is our formula for t observed. That's the observed value, the one we're going to calculate. It's the one we're working towards. And for each one of these, for this formula, something you need to know in order to be able to calculate it is this denominator. So here's the formula for calculating that denominator. If you don't know how to calculate everything here, look over here, because there's more. So basically it just keeps going down until you drill down until you get to the formulas that you have the stuff to do. And you work your way forward until we get over here. And we're going to practice that today. If we look at this formula, this is a mean difference, because remember, we've only got one group of subjects and they're going to do two things, right? So what we're going to do is we're going to calculate the difference in their performance between the two groups and put that in the numerator now. So it's the same group of subjects doing two things, and we'll calculate a difference in their performance. And then underneath, we're going to calculate estimated standard error based on the standard deviation for their performance in the two groups. Okay, so very similar formulas going from Z all the way down to T, really similar structure. You will be responsible for selecting what formulas you need. I will not tell you on the test which formulas you need to use. They will not be on the test. You are responsible for selecting the formulas you need and putting them on your note card. Okay, so you have to choose the formulas you need, and on the test, I'll give you a problem. I'm not going to tell you, do an independent sample t-test. You're going to have to go, I recognize that that's a between subjects design, I have to do an independent sample t-test. So one thing we're going to learn, we're going to practice, is being able to tell which kind of test you should do. And we're going to go through every step really slowly to learn the system that I have for doing the calculations. And once you get into that pattern, it'll be easy. And you can put those steps, all those things on your note card too. You can put a sample problem on your note card if you want to. You can put anything you want on the two sides of your note card. Motivational messages, whatever. But now you want to be thinking, starting today, what kind of stuff might I want to have on my note card to be able to do these kinds of problems independently on the test. All right. Does anybody have any questions about this chart? So you don't have to know, we're never going to calculate any Z scores in here. We're not going to calculate single sample T, but I included them because there might be some formulas up there that you learned when you were doing those that you're going to need for the stuff later on. So in case you don't remember those formulas, I put them up there for you. All right, so the way I do math, when I'm teaching math, is I do math by doing math. So I teach math by having you go through the steps. We're going to talk about how to do the single sample, how to do the independent groups t-test by doing independent groups t-test on data from a between subject study where that kind of analysis would be appropriate. So I'm going to give you, when we start to do a statistic, I'm going to give you a setup. Say, so here's kind of the experimental situation. Here are some data. Now we're going to go through all the steps that you would need to go through to analyze the data on a test, potentially, or for a practice problem. And we'll go through it step by step by step. So you'll want to have out some blank paper where you can write answers to these different things and use that as a guide when you're working on problem sets or any other practice problem. All right, so here's the setup. A researcher wants to know is doing research on factors that encourage young children to read. Because we want kids to read, and the best way for them to improve their reading is for them to read more, practice, practice, practice. Right? Practice makes perfect. So the researchers trying to figure out ways to keep the kids interested in what they're reading so that they will keep reading and get better. The researcher in this particular study is focusing on one very straightforward manipulation, which is putting the child's name in the book. In other words, having one of the characters in the book share the child's name. So you can imagine that if your name was Harry and your best friend's name was, who's Harry's best friend? Huh? Ron. You guys have read Harry Potter, right? You're hurting my feelings here. Huh? Draco. Yeah, I'm probably not going to meet a lot of kids named Draco, but maybe Drake could be Draco. You never know. All right, so reading that story is, if your name was Harry and your best friend's name was Ron, reading the Harry Potter books would probably be extra super cool, right? Now, I don't know how many people are going to have a guy named Harry, a friend named Ron, and a gal pal, Hermione. It doesn't show up a whole lot in the States as a name, but, something. All right. So he's going to have one group of kids read a story where all the characters' names match up with the kids in that sample. So the kids who read that modified story are Anne, Boris, Clyde, Dana, Eric, and Fiona, and those are the names of the characters in the book. And who knows, Anne might be a polar bear, and Boris might be a penguin, who knows? We don't know anything about the story, just that every kid in that sample has a character in the story with the same name. Now, the same book is also given to another group of kids. But for them, it's just an ordinary story because their names are George, Harry, Ivana, Justin, Kelly, and Lauren. So their names don't match with any of the names in the book. So for them, it's just a regular story with Boris and Anne and Clyde and Dana and Eric and Fiona. But that's not their name, so they don't have that same, ooh, it's me kind of connection. And the researcher predicts that the children who read the modified story are going to read for a significantly longer period of time than the kids who read the ordinary story. Now, they're both groups are reading the exact same book, but their connection to that book is different, right? Because if it's got their name in it, it's been modified for them. But if it hasn't been, then it's just an ordinary story. So we've got the time that each child spent reading. And what we're going to try to do is figure out whether this group did in fact read significantly longer than this group. Okay? Is everybody clear on the setup? No, notice these samples are really tiny. Right? They're very small. Optimally in a study like this, we would have much larger samples. Preferably maybe 30 kids in each sample if we could get them. That would be nice. But for the purposes of doing this problem, since we're going to be hand calculating everything, and I know you don't want to hand calculate stuff for 60 kids, that would be awful. It would take a really long time. We're just going to focus on these much smaller samples. So the first thing I want you to do every time you get a new problem is I want you to think about what the null hypothesis would be and what the alternate hypothesis would be. And when I ask you this, I'm not just asking for a general null hypothesis or a general alternate hypothesis. Because for any study you look at, the null hypothesis could be there will be no difference among the groups, right? Plus it doesn't tell me anything about the study, right? I could say that for any study, the null hypothesis, there will be no difference. And the alternate hypothesis for any study could be there will be a difference. Right? But that doesn't tell me anything. I want to know what the null hypothesis is for this study and what the alternate hypothesis is for this study. And in order to do that, I have to include some specific pieces of information in my answer. These are the things, when you come up with a hypothesis, that I want you to include. I'm going to write them so it slows me down so I don't talk too much. Okay. Number one. First thing, anytime you state a hypothesis, you want to make sure that you indicate in your statement what groups are being compared. And when you tell me in your statement what groups are being compared, you're showing me that you understand what the independent variable is and what the levels are. Because the independent variable is what defines the groups. And the levels of the independent variable define the groups. So you've got groups of subjects, and I want to know what groups are they. In this case, the groups we're comparing are children who read a story with their name in it and children who read a story without their name in it. Right? That's not too horrible. Second thing, I want you to tell me what is being compared about the groups. And when you can tell me that, you're showing me that you know what the dependent variable is, or if there's more than one dependent variable. In this case, what are we comparing about the groups?
Reading time.
Yeah, time spent reading. So somewhere in our statement, we're going to have to mention about how long they read. The third thing that you want to indicate in your statement is whether you are predicting a significant difference or not. Significant, I'm glad it's spelled. Now, in the case of the null hypothesis, the answer is always no. Right? So when you're describing a null hypothesis, it should be clear somewhere in your statement there will be no significant difference. In the case of an alternate hypothesis, you are predicting a significant difference. So you want to make sure that you are clear whether you're talking about the null hypothesis or the alternate hypothesis. When you do your description, it's always going to be no in the case of the null, and yes in the case of the alternate hypothesis. But your statement needs to say that. You have to clearly say, there will be a significant difference, or there will be no significant difference. I want you to be really clear about that. The fourth thing you've got to keep in mind is whether there is a predicted direction of the effect. Now, what do I mean by this? I mean, there's really kind of two ways you could go. If you're talking about an alternate hypothesis, you could predict that group A is going to have a higher score than group B, or group A is going to have a lower score than group B. You could make a prediction like that, a really specific prediction. Those kinds of specific predictions are called we'll give you a one-tailed test. Okay, so you have a very specific prediction about which group is going to be bigger or smaller or faster or heavier or smarter or whatever. When you predict that one is going to be something more than the other, then you've got a direction of the effect. The alternative is that you just say, I think the groups are going to be different, but I don't know how. I don't know which group is going to be higher, but I think one of them is going to be. I don't know which group is going to be lower, but I know one of them's going to be. That kind of more general prediction does not have a direction. Or it's bidirectional, because you're saying could go this way, could go this way. I don't know. That more general statement. So you need to know when you look at when you're looking at the summary, you have to figure out, is the researcher predicting a specific direction of the effect? Are they making a specific claim about one group having a score that's bigger than another group? Or are they just saying there's going to be a difference, but I don't know which way it's going to go? In this case, if we look at the summary, you can see that it says he's interested, or she's interested, he is interested in whether using a student's name in the story will improve attention span during reading. And that improve right there suggests that the researcher is predicting that the kids who read the story with their name in it are going to read longer than the kids who read the story that doesn't have their name in it. So that's a directional prediction. Now, when we talk about a null hypothesis, there's no direction. Null hypotheses never have a direction, because you're just saying there's no difference. And no difference can't have a direction. It just, because there's anything to have a direction.
Could you say there will be no improvement?
Mm-hmm.
Okay, but that's still not directional?
It's still not directional.
Okay.
Because nothing's going to happen.
Okay.
You're basically saying the treatment is not going to have an effect.
Okay.
So since the treatment's not having an effect, it can't have a non-effect in some direction. Right? It doesn't make any sense.
Yeah.
Right? Can't do that.
Yeah.
So, but you can say you want it, but if you have a specific direction, then you want to indicate what that is. And the last thing you want to make sure your statement for a hypothesis says is you want it to be, you want it to clearly indicate whether the comparison is between or within subjects. So, when you're describing the hypothesis for a study, I should be able to tell from reading what you write whether it's different groups of subjects that are being compared or one group of subjects that's being compared on different treatments. That should be clear from the way you word things. If you're too vague or you word it in an ambiguous way, then you haven't successfully described the study. Question?
Can you give an example just so you know that?
Absolutely. We're going to. I'm just giving you the rules now. We're going to generate a null hypothesis and an alternate hypothesis for this study we're talking about. Okay. So now let's think about. I asked you for the null hypothesis and an alternate hypothesis for this study. Null hypothesis. I'll give you an example of the null hypothesis that includes all 5 of these things. Something like, there will be no significant difference in the time spent reading by a group of children who read a book with their name in it and a group of children who read a book that doesn't have their name in it. Done. And it doesn't have to be just like that. As long as it has all 5 pieces of information in it, you're good. So you could break it up into multiple sentences if you want to. So the researcher is comparing 2 groups. A group of children that read a story with their name in it and a group of children who read a story without their name in it. He predicts there will be no difference in how long the 2 groups of children read. Or the null hypothesis predicts there will be no difference in how long the 2 groups of children read their story. Great.
Well, I was going to try now.
Okay. Yeah, I'm going to give you a shot. How about you do the alternate hypothesis?
I haven't written that down.
Huh?
I haven't written that down.
Okay. Well,
this one down.
okay, you try the null. Okay, try the null hypothesis first.
Okay, the study confirmed that the.
It's prediction, so nothing is confirmed yet. We haven't done any analysis. It's prediction. So the researcher predicts.
Null hypothesis.
Yeah, the researcher predicts, or the null hypothesis predicts.
The independent variable child's name being substituted for the character's name or not in the book did not influence and had no significant difference. Now, on the dependent variable, the length of the time that the child reads the.
I like how you included, like, this is the independent variable and the dependent variable. When you said this is the independent variable, you then gave the levels, not the variable. So you said the independent variable of, so you could say the independent variable of book type, because that would be the independent variable, and the levels would be modified story and ordinary story.
Could you say your original null hypothesis one more time?
How about if you try to do it, and I'll tell you how you do? Because I know I can do it.
So there will be no difference in the time spent reading.
No significant difference.
Oh, no significant.
Yeah, throw that significant in there. Because there could be a numerical difference, it just won't count.
There will be no significant difference in the time spent reading, depending on their.
I don't know who there is yet, because you haven't told me. So there will be no significant difference in the time spent reading by whom?
By the children. I had it in my head. And
That's okay, that's why we're going to get it out. It's okay, it's still in there. So what are our two groups? By children
Or in this story.
who read a story with their name in it, right? It's not actually the kids in the story, it's just that the character has the same name. So there will be no significant difference in reading time for children who read a story where a character has their name compared to. That's right. You got it.
Can we say just modified story or ordinary story, or do we have to explain what that is?
I don't know what those are. You haven't told me yet. It's a hypothesis. So I don't know what a modified story is. And that's the manipulation. But the groups we're comparing are the groups of kids who read that story. Now, you could reword it, I guess, if you wanted to, and say something like, there will be no significant difference in how interesting children find a story that it's modified to have their name in it, or something like that. But you have to be really careful when you do that, because you want to be clear whether it's between or within. So you can't say something like, there will be no significant difference in how interested children are in reading a story with their name in it or without their name in it, because that sounds like they're reading two stories and you're comparing two stories, and that's not what's happening. So you always want to be careful about that fifth thing. So, there will be no difference in how long, when comparing two groups of children, there will be no difference in how long the first group reads and the second group reads, even though the first group is reading a book with their name matching one of the characters, and the second group is reading a book with their name not matching one of the characters, or something like that. But the way you say it isn't as big a deal to me as long as you get all the points right. One sentence, two sentences, I don't care. So say it in a way that's clear for you. But APA style calls for you to be clear and concise. And if you're working in a research lab and you have to summarize, you have to indicate what the hypothesis is on a research poster at a conference, you need to be succinct. And including all those points in one sentence, maybe two, will make it very clear to the people coming to look at your research what you're talking about. This is the hypothesis. Okay, so that's the null hypothesis. There will be no difference in the reading time for children who read a story that has their name in it compared to children who read a story that doesn't have their name in it. That's a null hypothesis. Now the alternate hypothesis is just a little bit different. That's where we're going to predict that there will be a significant difference. And in the case of this particular study, we have predicted a specific direction of that effect. the researcher says, the researcher is interested in figuring out whether having the student's name in the story will improve their attention span. So that's a directional effect. And which group is supposed to read longer? The ones with their name in the story, right? So we can kind of modify what we said there. So we can say, children who read a story where one of the characters has their name will read for a significantly longer period of time than children who read a story where none of the characters has their name. Or something like that. And again, or something like that is important because it doesn't have to be exactly like that, but it does have to have all that information.
Can I give it a try?
You bet.
Children reading the story with their names will be longer than children reading the story without their names.
Good. The only thing I would add is put significantly in there.
Okay.
But yes, you got it. Go you.
Thank you.
So just remember you get all the parts. Now the great thing about doing this at the beginning, before you do anything else, is that it makes you think about what are the comparisons you're really making, what is it I'm really looking for, because obviously at the end, our statistic, after we do all the math, we have to decide whether we're going to retain or reject the null hypothesis, right? So we have to evaluate the null hypothesis. That's the last thing you do with any statistic. Well, if you don't know what the null hypothesis is, then how are you supposed to evaluate it? But once you do, once you decide whether you're going to retain or reject the null hypothesis, then you can, so say you decide to reject the null hypothesis. Because if your null hypothesis says there will be no difference in how long children read, if they are children who read a book with their name in it or children who read a book without their name in it, no difference. Well, if we get a difference, then you know it's not that, so you reject that one. And then you've got this lovely alternate hypothesis already done, right? Children who read a story with their name in it will read for a significantly longer period of time than children who read a story without their name in it. Well, heck, that's practically the results section already written for you. All you got to do is change the verbs. And it becomes children who read a story with their name in it read for a significantly longer period of time than children who read a story that didn't have their name in it. So basically, you can have your results summary written if you just think about what the hypothesis is ahead of time. And that way you're totally clear on what it is you're looking for when you do the math. Right. Does anybody have any questions about this? You got your 5 things down? All right, so the next thing we have to do on here, it says, will you use a one-tailed test or two-tailed test to analyze the data? Well, you have to know, because you don't know which kind of test you're doing. You don't know how to look up the critical value, so you can't, this is the next question you've got to answer. So how do you know if you're doing a one-tailed test or a two-tailed test? I'll give you a hint. So if we look here at the distribution chart for T, this is the table that we use to look up critical values. We have to know whether we're doing a one-tailed test like this, where we're only going to look in one of the tails of the distribution, or if we're doing a two-tailed test like this, where we can look in either one of the tails of the distribution. How do I know?
By the direction?
That's right. It's by the direction. So we look at the alternate hypothesis. And if the alternate hypothesis has a direction, if the researcher is predicting specifically that one group is going to have a higher score than the other group, or one group is going to have a lower score than the other group, they're making that specific prediction, then it's a one-tailed test. Because you can think of that specific directional prediction like a spotlight. It's going to focus the attention on one end of the distribution because you're pretty sure that's where you're going to find your answer. You're just going to ignore the other part because you don't think, you're really pretty confident it's not going to be over there. Two-tailed test is where you're not sure which end, so you're basically covering your bases. I you think that it's going to be different, but you're not sure how it's going to be different, so you look in two places. The example that I used in my last class was, say you reach into your back pocket to grab your phone and you realize it's not there. Now, if you pretty clearly remember that 10 minutes ago you had your phone, you went into the bathroom in your apartment, your house, and you took it out of your pocket and you set it next to the sink because you did not want to have the classic accident of having your phone fall out of your pocket and into the toilet. So you take it out of your pocket and you set it by the sink. And then you forget to put it back in your pocket when you leave the restroom. Well, if you put your hand back there to get your phone and all of a sudden you realize it's not there and you're like, oh, well, I had it in the bathroom, so I'm going to go look in the bathroom for it, right? I took it out of my pocket there, I remember, so I'm going to go look. Okay. That's like a one-tailed test. You know where to look for the thing that you're looking for, right? So if you wouldn't then say, I'm going to go look in the kitchen for it. I'm going to go look in the bedroom for it. I'm going to look in the living room for it. That would make no sense, right? You know where you want to look. You know where you had it last. So you're going to go look there. That's the one-tailed test. If you've been home for a while and, last night maybe you went out and you partied a little hard. You get up in the morning and you're looking for your phone and you don't know where your phone is because you kind of don't remember what you did with it and you're not sure where you should look. What do? You check the bathroom, check the kitchen, check the living room, check your car, right? Please, hopefully you didn't drive your car if you couldn't remember where your phone was. But if you're not sure where to look, you look everywhere. Right? That's like a two-tailed test. So you can think of it like this. A one-tailed test is like a spotlight. A two-tailed test is like you don't know which one. Visual aid. Okay, you're not sure. So in this case, because of the directional prediction of the alternate hypothesis, we're going to do a one-tailed test. Does that make sense? We don't have any reason to look down in the negative end. We're expecting that experimental group of kids who read a story with their name in it to have a significantly higher mean reading time than the other kids. So we expect their score to be up in the positive end of the distribution. So that's where we're going to look. So we're going to do a one-tailed test. Does anybody have any questions about why that's true? You okay with that? Okay. Now the next thing on our list, it says, given an alpha level of 0.05, what t-score will define the boundary of the critical region or regions for our hypothesis test? In other words, what is the value of t critical? Now this, if we're thinking about this picture right here, t critical is whatever numerical value defines that boundary right there between the normal part of the curve and the critical region. If we're doing a one-tailed test, we just have one value. If we're doing a two-tailed test, we have two values, one for the negative end and one for the positive end. So now we have to figure out how to look that up. Because before we do anything, we want to know what our t-critical value is. So take a look at this chart. What kind of information do you have to look up a t-critical value? What does the chart tell you? If you're looking at this, we've got to know degrees of freedom, right? Because clearly I'm going to need degrees of freedom to know what row. And then how do I know what column? Alpha. I need to know what my alpha is. Is that enough? What else do I need to know? One more thing. One or two tails. Because if, for example, I have an alpha of 0.05, I could need this one, or I could need this one. Because both of those are 0.05, I have to know which one I need to use. In the case of this study, which one do I need? The top or the bottom?
Top.
The top. This one right here, right? Proportion in one tail, because we're doing a one-tail test. So we know that this is the column we're going to need. That's the column we're going to need. Now we have to figure out what row we need. So got to figure out what degrees of freedom is the right degrees of freedom to use for this test. All right. So, you guys remember from 3510 calculating degrees of freedom as the sample size minus 1? Remember doing that? Okay, that's one of the more basic formulas for degrees of freedom. There's actually lots of different formulas for degrees of freedom, depending on what statistic you're using. This is how we calculate degrees of freedom for a single sample. But in this study, we don't just have one sample, right? We have two. We have sample 1, and we have sample 2. And so we're going to start off by calculating the degrees of freedom for each one of those samples. So the degrees of freedom for sample 1 is going to be sample 1 minus 1. And the degrees of freedom for sample 2 is going to be sample size 2 minus 1. And how big is my sample for sample 1?
6.
So that's 5. And for group 2, same. Right, so now I've got the sample for each group, but that degrees of freedom thing over there doesn't have degrees of freedom 1, degrees of freedom 2 on the chart. It just says 1 degrees of freedom. So what should I do? Well, in the case of the independent samples t-test, what we're going to do is calculate a new thing called degrees of freedom pooled, which is written as df subscript p. Every time you see that lowercase p as a subscript, that means pooled. And what do you do when you pool things? Like, say you and your friends want to get a pizza, and you decide you're going to pool your resources. You add them up. You like, I've got $5, I've got $3, I've got $6, I've got $8. Okay, we got enough to get a pizza. Maybe a 2-liter. Right? No, I want a brownie pie. No, I want a 2-liter. Shut up, I have more money. You have to do what I want. Right? That's how it works usually. All right. So to calculate degrees of freedom pool, we're just going to add the degrees of freedom for our two groups. And this value right here, that degrees of freedom pool, that's the degrees of freedom. I refer to that as the DF critical, meaning that's the degrees of freedom you need to look up the critical value. That's the one that you need to use the chart. For the independent samples t-test, that's the one you have to get to first to look it up. So, if you know that our degrees of freedom that we need for this table is 10, what do we know now? Well, we decided that we were going to use alpha's 0.05. We're doing a one-tailed test. So now I'm going to follow it down here, and I go over to degrees of freedom 10, and I'm going to go across, across, across. Tell me where to stop. Right there. Right there. 1.812. 1.812.
And this is our T critical?
Mm-hmm. Positive 1.812. Now, here's something I want you to remember for this class. That is that we always round everything to 2 decimal places. We round early and we round often. Okay, you round every single step, not just when you get done with the calculation, every single step. And we do that because our alpha level is 0.05. Our alpha level is to 2 decimal places. So we are going to round all of our numbers to the same 2 decimal places, so we're working at the same level of precision as our alpha. So that means that to round this properly for this class, we would change this to 1.812. 1, and that would be the answer. That's the number we've got to hit, 1.81. So that's our critical value. We need to beat that number with our t observed, the value that we end up calculating for our study data. We need to have a t observed that's bigger than that number, more extreme than that number, in order to have a significant difference in our study. Is everybody clear on where this number came from? And everyone's clear on why it rounds to that? Yeah, question?
I just had past math teacher that told me you want round at the end to minimize as much error as possible.
That's true, but when we have lots of people who are doing math at the same time, people end up rounding at different points in time. What they think is the end is at different points in time. So the strategy that I've developed is we just round always. Round every single number. Another advantage of doing that is it makes you stop, because when you have a calculator, some calculators will just keep doing, you can just keep punching in numbers and it'll just keep doing the calculation. And when people get in the habit of doing that, they don't stop at each step and think about what they're doing. So if they have bad numbers, it just cascades into a big pile of mess. So if you stop and round every number, it makes you have to stop, hit clear, and type all the numbers in again, as opposed to just letting your calculator hold them in memory and continuing to do more and more calculations on them. And by doing that, when people are learning, if they hit a place where they're making a mistake, I can actually see where they made the mistake. As opposed to if they just start punching numbers in their calculator and come up with a final answer, and it's wrong, I have no idea where it went wrong, because they didn't stop at each point. So as a just to practice, so that to slow people, I'm literally trying to make you do the math slower, because I want to make sure you know what every step is and that you show me what every step is. And that's just one way to do it. So that's my reason. I'm not trying to torture you. We will get some rounding error, that's true, but with the practice problems we do, that rounding error never ends up being the thing that keeps us from getting a significant result, because it's tiny.
If the alpha level was 0.1, would we round 1 decimal place, or would we still round 2?
It would be to 1 decimal place, but we won't ever use 0.1. We'll use either 0.05 or 0.01. So 2 decimal places all the time. But in general principle, Corey, I agree with the math teacher that says round at the end because you want to get as little rounding error as possible. But when I have lots of people end up rounding. I can't say, so what's the answer for right here? And people have 17 different answers if they're rounding in different places. We all want to get the same answer. Yes?
And you're going to provide either 0.05 or 0.01?
Yes, I will provide it the default. If you don't see anything in the problem that tells you what alpha is, assume 0.05. So you don't have to say, I don't know what the alpha is. It's 0.05 if it doesn't otherwise say. But if it does say 0.01, don't use 0.05, because then you'll have the wrong answer. All right. The next thing says, all right, calculate the degrees of freedom, the mean, the sum of squares, and the variance for each sample. Well, we already did the degrees of freedom because we had to do that to figure out the degrees of freedom critical. So we're good to go there, right? We already figured it out. Degrees of freedom is 5 for group 1 and 5 for group 2. Score, we don't have to worry about that one. Skip. Okay. But it says the next thing we need to do is the mean for the 2 samples, the sum of squares for the 2 samples independently, and the variance. So let's write that out here. We need the mean for group 1 and the mean for group 2. And we need the sum of squares. What's the mean for group 1, for the modified story group? What's the mean? Break out those calculators. I'm gonna do math. Okay, so if we're rounding 2 decimal places, what is it? 10.33. We have confirmation. Somebody else get that too? You see some heads nodding, thumbs up. Okay. What about for group 2, the ordinary story group? What's their mean? around 6? Okay, excellent. Now it says we need the sum of squares for group 1. You guys all remember how to do sum of squares, right? Vaguely, kinda, sorta, not exactly. Okay, well, let's bring in sum of squares for group 1, sum of squares for group 2. Well, sounds like we need to do some more math. All right.
Oh, don't you square every single number and then add them all up?
Almost. So to do sum of squares, I'm going to get a new piece of paper. All right. So sum of squares is shorthand for the sum of squared deviations. Okay? A deviation is when you take a score and you see how far away it is from the mean for the sample that you got it from. That's a deviation. How far does it deviate from the mean for the group? And you do that by separating by subtracting the mean from that score. So in the case of the modified story group, we have Anne, Boris, forget their names, Clyde, Dana, Eric, and Fiona. Look, it's almost like I planned that. And we know that Anne read for 4 minutes, and Boris read for 16 minutes, and Clyde read for 11 minutes, Dana read for 9 minutes, Eric read for 8 minutes, and Fiona read for 14 minutes. Okay, so we know that that's how long each of them read. We figured out that the mean for this group was 10.33, right? So we're going to calculate the deviation for each child. We're going to calculate the deviation for each child. Then that's going to be 4 minus 10.33, right? What does that equal? What's 4 minus 10.33? I have a vote for negative 6.33.
Yep.
You agree? And then this one's going to be 16 minus 10.33. What's that equal? I have a vote for 5.67. Confirmation? Yes? Little tiny voices. Go for it. We're subtracting 2 numbers. That's a good one. 5.77, 5.67.
6.7.
6.7. Okay. 11 minus 10.33. 0.67. Okay. And 9 minus 10.33. Negative 1.33. Yes. 8 minus 10.33. Negative 2.33. And 14 minus 10.33. 3.67. Okay. So these are the deviations. Those are the deviations. Now, the deviations tell us about how far away each score is from the mean, right? Since the mean is like the balance point, it's right in the middle. That means that if we add these up, what should that number be close to?
0.
0. Now, it might be a little bit off from 0 since we're rounding. We could have a little bit of rounding error. But if you add up these scores, what do you get? If you add negative 6.33 plus 5.67 plus 6.7 minus 1.33 minus 2.33 plus 3.67, what do you get?
0.02.
I have a vote for 0.02. Yep. So that's pretty close to 0. We've got a little bit of rounding error in there. I can live with it. But someone last time said, if we're not going to use that number for anything, why do we calculate it? Because we all know we don't want to waste any time doing math that might not be useful. And I completely agree with that statement. We should not waste our time doing math we don't need. So here is, this number right here is basically a check number. It's a number you want to check to see that it's 0 or very, very close to 0. Because if this is something like 0.7 or 1.2 or some negative 3.8 or something like that, then there's something really, really wrong with the math in that column. And you need to go back and you need to stop and do it over, check your work, because something is wrong. And if you're already wrong here, nothing you do after that can be right. There will not be, you can't rescue yourself from messing up those deviations. So you have to, this is going to be the basis of everything else you do. So it will basically it will make every other answer after that wrong. So I will always try to highlight for you places where you can check your work to see if you're on the right track. So you know if you're potentially in a problem zone where you might want to go back and look at your stuff again to make sure you've got it right. Because you might have missed a plus or a minus or something like that, and those are important. So you want to make sure that you double check. So this is a check number. Right. So now that I've got that, I need to square those things. So I'm going to square them. Square those deviations. So what is negative 6.33 squared?
$40.07.
Okay, we'll vote for 40.07. Yes, thumbs up. Okay, what about 5.67 squared?
32.15.
I would vote for 32.15 and a thumbs up. I feel like I'm at an auction. People are just kind of like, they're doing these little tiny gestures. It's like, it's okay if you be like, that's what I got too. And if you get something different, please, please, please. It's important for you to do these steps. I know I see some people doing it and some people just waiting. You want to practice doing these steps now, where we have some confirmation, because the people who are shouting out answers cannot do your math for you on the test. So you want to know now if you're getting the right answers, not later. All right, so give me that 5.67 number again. 32.15. Okay, what about 0.67?
0.45.
0.45? I promise I won't bite you. Yes. I should just give everybody paddles. All right, negative 1.33. 1.77, yes. And negative 2.33 squared. 5.43. Pretty soon, when people start to get more confident, it becomes a choir in here. It's awesome. Where everybody's all saying the same number at the same time. It's pretty neat. You're like, I got it. Okay, 3.67 squared. I have a vote for 13.47. All right, so now that I've got those, now I need to add those up to get my sum of squares. Right? Now I need to sum those. So go ahead and add those up. I have a vote for 93.34. Warren says yes. All right. So this is our sum of squares for that first group. Now, I said I also needed to calculate the sample variance for that group. Do you guys know how to get sample variance from sum of squares? Do you remember? No.
Take the square root? No.
Yes?
I got a different sum.
Okay.
I mean, it's literally like 20 off, but I kind of the same. I got 33.31.
Okay. Did you round at every step just like this? Every single step? So if you go back in and hand type 40.07, 32.15, 0.45, 1.775, 0.43, 13.47, if you hand type each one of those in, what do you get?
I think I know where it's stuff
Yes?
What was the purpose of adding that first part?
This check, you want this to be 0 or very, very close to 0 so that you can check in to make sure that you did your math right here. It's just a check. I find when I'm doing lots of hand calculations, and I'm a nerd, so I actually do, that I want to have places where I can look to see if I'm on the right track, especially if I'm just learning how to do a new thing, so that I can, okay, that makes sense, all right, I probably haven't screwed it up yet. That's one of those, let me see if I screwed it up yet. And pretty soon you get good at it, and you're like, yeah, okay, that's fine, that's fine, that's fine. And so then you start to feel more confident, because your check numbers are telling you that it seems like I'm on the right track. Okay, so do you know where the 93.34 came from? Are we good? All right, so when we want to calculate sum of squares, we want to calculate sample variance, that is sum of squares over degrees of freedom. So you want to take a wild guess. If I'm trying to calculate the sample variance for sample 1, what the formula is going to be? The sum of squares for group 1 over the degrees of freedom for group 1, right? That makes sense. So that's going to be 93.34 over 5. And what is that?
18.67.
Okay. So, your mission, should you choose to accept it, is before class next time, calculate the sum of squares and the sample variance for group 2 and come in with that information. If you've already done it because you're super fast, she's like, I already did it, then you're done. All right. You guys have lab today, right?
Yes.
Oh, yes, you look at those tests. Okay, so go forth and be awesome, and I will see you